everyone. In this video, we are going to be deriving the Carnot cycle and explaining what that is as we go along. So the Carnot cycle is a frictionless reversible theory for heat engines. And I'm going to draw this graph of the Carnot cycle over here so I don't have to write around it constantly for the remainder of the video. So it is a volume on the bottom, volume on the x, pressure on the y, and it runs at two temperatures. Runs at T equals TH, runs at a hot temperature, and it runs at a T equals TC, a cold temperature. Okay, and it starts at A, and then it makes its way down to B, and then it switches temperatures over here to C, and then it runs its way up back to D before it slowly meanders its way back to A. So what I'm going to be doing is breaking down each step. So when it goes from A to B, the temperature is constant. When the temperature is constant, that means there's going to be no transfer, and which means that our, what was I trying to say there? Our temperature is constant, yeah. So that means our change, or our dt equals 0. And so what we know is that du equals dq minus p dv. All right? And also, something else we know is that pv equals nRO. Again, everything what we're doing today in this video is for n of 1. So PV equals RT. And with what I said earlier is if the temperature remains at the hot temperature, that our du, otherwise known as CV dt, it equals 0, as there is going to be no change in temperature. All right? And, oh gosh, my computer is really loud now. And now we're going to have dq. So we're going to have dq minus pdv, which ends up equaling dq equals pdv, which we know as RT over V. So it's going to be RT over V dV. So now we're going to take the integral with respect to V1 and V2, with V1 being A, or we could do VA and VB if we really wanted to. Then we would do respect to here with the Q with 0, then the Q, as the Q is the temperature, or not the temperature, excuse me, is the heat. All right? So we would end up adding Q equals R, and then T, which we know is a constant in this scenario, as it's TH, would be R, TH, then ln of VB over VA, or V2 over V1. All right? And now I'm going to draw up the situation real quick right here. So what we have here is A. And what A wants to do with the QC and temperature being constant is expand. As you can see on the graph, it goes along the x-axis, which is volume. And for it to expand without without changing its temperature, it needs to do work on the system. And so our VB, from VA to VB, it does work on the system. So if we were to have a single action engine, and we could replace them as much as we wanted, this would be a perfect engine, as it would go from A to B and give off all of its work. And so from there, we would basically be done. And that would be a shot engine, and you have to scrap the whole thing, and then we'd have to restart from scratch. So the cycle kind of reduces that fact. So now that we've gone from, this is A to B, so it's A to B. Now we want to go from B to C. And what we want to do from B to C is we're just going to go adiabatically, which means our dq, or our heat, or change in heat, is going to be 0. And so, here, let me do this real quick. So I'll actually draw out the situation first this time. So we have our expanded and hot cylinder, and we want it to go to a cool temperature. And so to do that, we're going to say adiabatic, where it's well insulated. And what that's going to do is very slightly expand. However, it's also going to go down to the cool temperature. So it's going to go from TH to TC. And what we're going to do is we're going to derive it now. So we would have du equals dq minus p, that's an R, minus P, right? Yeah, minus P dV. And with du equaling 0, as we know, that this would have to turn into CV dt equals negative, and then what we did over here, it would be RT over V. And with T changing, we're going to want to bring T over here. So we would have negative R over V, dV, remember don't forget the dV, and then that would equal CV, then dt over T. And I'm putting CV off to the side because CV is a constant. So then we would integrate with respect to, I believe this would be T1 to T2, or we would start at TH and we would end at TC. That's important. And from here, we would also integrate this side. I believe we could pull the R out. We would integrate from VB to VC. And what we get here is actually the start of a rabbit hole we've already done in homework A. And so what we end up getting is TC over TH to the power of, let's see, CV over R, and that ends up equaling VB over VC. All right? And so we end up getting this right here, as VB over VC is that constant that we talked about earlier, with how you could always have the temperature over the temperature to our heat capacity, and it would always give you that constant number. So now I'm going to erase this part over here. Actually, I will write this over to the side, and then I'll erase over here. Actually, I'll write both of these, and then I'll start writing through. As that way, we can then go from C to D and D to A, which are similar steps. So from A to B, it is Q equals RT H ln of V2 over V1. And another thing I wanted to talk about was that, I want to make sure I didn't forget, is for this to expand, with there to be no heat added, that means it has to take in energy and take in heat, or it has to expel that heat, which makes it cool down from TH to TC, all right? And that's A to B. And now from B to C, we have TC over TH to the CV over R, and that equals VB over VC. So this may seem strange, but it all is important in the long run. All right. So now what we want to do is we want to go from an expanded cold cylinder to a compressed cold cylinder. And we're going to be doing that again by doing that isothermically, as we don't want the temperature to change. So we want to go from C to D, in which I believe the only difference would be a negative sign. So we would, but I'm getting ahead of myself. So we would have du, and remember again, everything is reversible. We would have du equals dq minus p dv. All right. And again, what we realized is if the temperature is going to be constant, like we did earlier, this is going to be CV dt, which then equals 0, and we end up getting dq equals negative p dv, and we know negative p in terms of reversibility equals negative RT over P. All right, and something again I also wanted to relate to earlier, but I think I forgot, is that when we do V2 over V1, otherwise known as VB over VA, it's that because it's an ln, we know it's going to be a positive number as V2 is greater than VA. As on the graph of ln, if it's less than 1, and the inside of the ln is less than 1, it's going to be a negative number. But if it's greater than 1, it's going to be positive. So that's how we can make sure we know that this is actually expelling the work that we want. But in this case, we would get this equals dq, and don't forget dv. Forgot v again, so that's okay. Integrate with, this would be from T1. This would be from 0 to q. So we would then have q equals negative RT to the, let's see, we're going from C to D. So from C to D to the ln of, let's see, C to D, so it would be C over D. But because we have a negative here, we can actually flip this. So it would equal RT ln of D over C, if we know to keep this negative. So what we would have here would be the QC, or the heat, the cold, would equal R times TC, as this is the cold temperature, to the ln of VD over VC, which we know to be giving us it's going to be a negative, or a negative amount of work done, so we can get back up to this D step. So we would have QC, so we have, it's going to be C to D as QC, and I know you can't read this, but I'm just, again, writing this down, so when we start going into the more of the algebraic steps, it's all right here so I can look back to it. So QC equals R TC, then to the ln of VD over VC. Then I'm going to change the V2 to V1 we had in A to B to VB over VA, just because I don't feel like messing that up again. So now, we want to go from D to A. It's almost the exact same from when we went to B to C. But first, I again forgot to write down what this looks like, so I'll do that again. So what we're going to have here is this is going to be C, and we want to go isothermically to D. And to do so, if we're not going to be giving it any heat, we're not going to be giving a change in temperature, which means we're actually going to have to give it some heat. And so it's going to be taking away some of the work that we actually gained from A to B. All right? And from there, so this is going to be D. Now, we can go from D to A, or at least we can attempt to. So from D to A, it would be almost the exact same thing as what we did earlier. As I will set it up, and then I will skip all of the integration and algebra that we've already done in this homework set. So we would have du equals dq minus pdv, which then we would have cv dt, because this is changing temperature, but we want to keep q as 0, as we want to do this adiabatically or well insulated. So that would then equal 0 with negative pdv. And we know, again, through a lot of practice, pdv equals cv, and then we're going to do 1 over t dt equals, let's see, it would be r over v to the dv. Then we would integrate, and what we end up getting is th over TH over TC to the CV plus R equals VA over VD, I believe. Let's look. That would be VD on the bottom. Yes, it would equal VD over VA. And so from here, we've calculated the full step around the Carnot cycle. So now that we've derived each step of the Carnot cycle, we can start looking at the different interactions between the two. First off, we're going to look at the interactions between the two equations that got us from B to C and from D to A. And if you notice, this is T over C to the TC over TH to the power of CV over R equals VB over VC. But what happens if we flip that? So what happens if we did TH over TC to the CV over R? That would equal VC over VB. As all we did was flip the inside, which means we would flip the outside. And if you notice, TH over TC to the CV over R is the exact same thing as what we have up here. However, that equals VD over VA. So what we can write is VD over VA equals VC over VB. Voila. This is huge, because from here we can do VD times VB equals VC times VA. And what we want to do is we want to get VC over VD. Right? Yeah. So VC, so then we get, if we do VC over VD, it ends up equaling VB over VA. So you're telling me that the inverse of this, or the inverse of this, equals this. And so what we can do is we can plug this son of a gun in here. If we go like -1. And if we switch that, that means we bring a negative out here. So we then end up getting, oh, my shoulder is sore. QC equals negative RTC ln of VD over, not VD, we just did this, VC over VD, or otherwise known as VB over VA. And what do you notice? We have this with the same ln as what we have here. And the work done by the function is otherwise known as QH plus QC. And then we want to divide by QH to get the efficiency of our function. Okay, and that equals the efficiency. And if we were to plug this in, we would have negative, we would have R minus R, so the R gone. We would then have TH minus TC all over ln of VB over A, all right? And the VBs would cancel, which would mean this would be all over TH. And there, this is the efficiency. Or you can even simplify it one step further, and you end up getting 1 minus TC over TH equals the efficiency of the max efficiency of a heat engine. And this is important, as this is like the greatest, not greatest theory that ever lived, but it's a theory that has driven a lot of things like cars or automobiles. And for us to be able to calculate the max efficiency, or basically any efficiency of any heat engine, is huge when determining what works and what doesn't. So now we're going to talk about how what we just calculated motivated the entropy definition. And so it first came about by someone realizing, oh, you can have any type of graph or cycle if it looks like this, looks like what we had earlier. And then from there, you can break it up into adiabatic and isothermic steps. And eventually, you can break it all the way up, and then you take the integral to get the area under the square curve. You take the integral of dq ref or all of the heat added up, and then you add, or then you divide by T, the temperature all these steps were done at. And they found that that equals 0. And it's very interesting and new. They're like, oh, but how is this possible? How is it we go from point A to point B? And so they decided to call this equal ds, which is entropy. So we have ds equals dq rev over t. We take the t to the other side, so we would get t ds equals dq rev. And if you remember, dh equals, dh equals dq minus pdv. And we realized, oh, we have dq rev. We can plug TDS into it. So TDS minus PdV equals DH. Not DH, it equals DU. Oh my gosh, man. So DU. All right, and remember, TDS is the temperature multiplied by the entropy. So now we're going to take H, or the enthalpy, I believe. So we have H equals U plus PV. So if we want to take the derivative of said, we would just do, d whatever. We would get dH equals du plus, now we have to do the product rule. So it would be P dV plus, and it would be V dP. And we kind of just shove these on top of each other. And what you end up getting is TDS minus PdV plus PdV plus VdP. Man, it's an interesting combination. So you end up getting TDS plus VdP equals DH. And this is a very important concept for entropy. Entropy. And that discovery in which they decided, or they found with entropy and creating it, is they also found a way to start relating to Gibbs energy. And the second law of thermo, or something along those lines, is the ds, or the change in entropy, plus the ds of the change in entropy of the surroundings is greater than or equal to 0. And this is because of all the work, every time you're doing a force or a work in the system towards the surroundings, there's also force being done on surroundings. P external, everything is different. Everything is like convoluted and conjoined. And so they found that this law would create that. Was the best way of explaining that. And it's also a way to start getting you to Gibbs energy. And what you would do is, we know that ds of the surroundings would be negative dq, and it's negative because of it was being done on the surroundings. So now if it's being done on it, it's going to be negative. dq over t, it's going to be ds is going to be greater than or equal to 0. Yeah, and then we're going to multiply by t. So we would get TDS minus dq rev greater than or equal to 0. And now that we have ds, or we have negative dq rev, we know that dq rev can't actually be something else. We know that du equals dq rev minus p dv. So we're going to shuck that thing in there. So we would then get TDS minus, I'd have to flip this around real quick. If it's dq rev, we would add that to the other side. This would be negative. Yeah, so we would have negative du plus pdv, right? If we want to have negative dq rev, so we would add that to the other side. So we would have, those would both be negative, sorry. Yeah, those would both be negative. So then we would have d, right? Yeah, we'd have negative minus du minus p dv. And this is still greater or equal to than 0. And now what we can do is we can start plugging or putting some of our functions or variables into our differentials. So our t will go into here, and our p will go into here. So we'll actually have d, actually everything will have a d in it now, or the differential derivative, so we can take that. So we'd have d to the t s minus u minus pv. Right, and that's still greater than or equal to 0. But we don't like all of these negative signs, so we're going to flip the sign. So we're still going to have the differential of u plus pv, and then we would subtract ts, and that is less than or equal to 0. And u plus pv is actually big H, or enthalpy, sorry. So then we would have the d of H minus Ts greater than or equal to 0. And this is otherwise known as the d of Gibbs energy is less than or equal to 0.